I wanted to go ahead and get started right away. I mean, it's 11:03, 11:04, but we have another big lecture, so wanted to get started, get through it as quickly as possible so that we don't go over. I hate keeping people over. But remember last time we started talking about explicit allocators, and we call them explicit allocators because the program is responsible for releasing the memory that it allocates. We also had implicit allocators, which were able to just focus on allocation because the allocator itself takes care of identifying when memory is no longer in use. But we won't be talking about that till next week. We identified a number of issues that allocators have to contend with, and the most notable one is fragmentation. Fragmentation is a really severe issue that can affect longer running programs. And I'll talk a little bit more about that because I want to make sure you understand what the challenges are that allocators have to deal with. It affects you as the user of an allocator. And that's why it's so important to understand. Also, coalescing adjacent blocks of free memory. This helps avoid false fragmentation where we think we don't have enough memory, but we actually do. And then also data alignment, which is a problem that allocators in the real world have to deal with, but your assignment 3 allocator does not have to deal with fragmentation. With data alignment, you do have to deal with fragmentation in some basic way. But certainly your allocator is not required to deal with data alignment. Okay, so we talked a lot about that. This was the common interface, malloc and free. We've talked about that with in a couple of lectures now. We also have a few other ones that sometimes you'll see implemented. Realloc is really common. Who here has used realloc? Anybody here use realloc? It's really powerful. You'll see me use it in like Lab 4 if you look at some of the code that I provide for Lab 4. It's really powerful because you can say, I want to take this chunk of memory and resize it. And so if you make it larger, obviously the old stuff is kept in the new chunk. If the allocator is able to extend the size of the allocated region, then it will. But it may have to simply reallocate a new chunk that's the new size and then release the old chunk. But it copies the data over that was in the chunk of memory. So that's why it takes a void star and returns a void star. And realloc is one of those interesting functions where you can allocate and free and reallocate all through this one function. So realloc can actually do malloc and free. Whatever, people don't do that because it's confusing. This is a very common way to represent blocks of memory on the heap. And you'll notice we have these various regions, which we'll talk about. The header basically is the allocator's details that it needs to keep track of the allocated block. So like I say here, total block size in bytes, including all the parts, tends to be very common. Some way of indicating whether or not the region is allocated or free. So it might be just a flag, or you might be able to encode that in the block size. You have various options. And as I was mentioning before, since the allocator frequently will hand back chunks of memory that are word aligned or D-word aligned or maybe 16-byte aligned, depending on the implementation of the allocator, you have certain bits in the address that are not going to be used. And you also have certain bytes in the size that are not going to be used. Because if you always are going to have a multiple of 16, then like the bottom 4 bytes aren't going to be used. Bottom 4 bits aren't going to be used. And if you have these bits available, you can use them to encode information, and that allows you to be more efficient. The whole idea being that if you have a certain payload size allocated and you have some overhead that you need to represent that payload is in use, you'd like to keep that overhead as small as possible because that'll make your allocator more efficient. Okay, so the payload is the area that the program uses. So the part in green, that's the part that the program asked for, and that's all the program is really allowed to touch, but it can do whatever it wants with that memory. And then the padding is any space that is necessary to append onto the end to make the whole thing the appropriate size. And so we may tack some padding on just to make sure that everything lines up properly in our heap. Okay? Any questions on any of these chunks? It's pretty straightforward, yes. The header is basically as large as the allocator requires. So it depends on the complexity level of what the allocator wants to do. Really good allocators will have either small or non-existent headers. And the allocators that we write in CS24, probably that'll be 4 to 8 bytes. Like in the end of assignment 3, I give you a really simple approach you can use for implementing the allocator for the assignment. And if you follow that, you can do it in 4 bytes. You could even do it in 2 bytes if you really cared to, but that's too limiting, I think. Because, you know, if you have a 2-byte header, then you really can only represent that the thing has, you know, up to 64K of memory or 32K of memory, depending on how you do it. And people frequently allocate much larger regions than that. So I would say that probably at least 4 bytes. OS 10 has a crazy allocator where it needs no bytes for the header, or where it actually needs like 2 bits for the header, which is crazy. But we won't talk about that. Okay, so memory blocks. So the program requests memory. The allocator is working with its headers. It has some structure that it imposes on the heap, and so obviously it's looking at headers, and so it'll have pointers to certain regions of memory, and those things will be header stars or whatever you decide to treat it as. So it goes ahead and manipulates these things, and then when it returns a pointer to the program, the allocator is like, well, I don't want to give it a header star because I don't want it to know or care what size the header is or what's in the header. So what it does is it does a little bit of pointer arithmetic to make sure that it returns a pointer to the payload. Because if you think about it, the program really doesn't want to think about that anyway. Ouch. The corner there. So, yeah, so basically, you might imagine if I have a header star, then I could just do, you know, H plus 1, so add 1 to the header star, and that'll move me forward 1 header, and that's exactly where the payload starts, and I can just cast that to void start, and I'm done. Okay? So, really easy approach for dealing with this. Now, some of you may have encountered this. What happens if the program decides, actually, I don't want to stay within the payload. I said I wanted 24 bytes, but I decided to write to 30 bytes. What could happen in that situation? Has anybody encountered this kind of bug before? One person? All of you will eventually. You're not necessarily going to get a seg fault. Not right away, anyway. And this is the problem with this kind of bug. Heap corruption issues frequently don't show up right away. Because imagine that you write into the padding. Well, in that case, who cares? The allocator doesn't care. Your program doesn't care. Somebody should care, but you really are being naughty. Okay? But a lot of times, if you're going before the payload or you're going past the payload into the next header, that's where it really starts to matter, then you can corrupt the heap. And the issue that you have is that these issues manifest in the next call to malloc, or the next call to free. And that's the thing that's really frustrating. When I have students implementing Lab 3, a lot of times I'll get emails saying, I'm trying to debug this issue, the seg fault, and it's crashing in malloc, which is clearly not what I wrote, because the function you have to write is myalloc and myfree. And then it goes and crashes in malloc. Why is it crashing in malloc? Well, probably because you're not staying within the memory pool size. You're probably going beyond it somewhere and trampling the real allocator's headers. And it gets really confused and then crashes. Okay? Any questions on that? Because you will run into, I mean, I shouldn't say you will. It's quite possible you will. I wouldn't be surprised if a significant percentage ran into that. Okay, when a program frees memory, so remember, the program has the payload pointer, so a void star pointing to the start of the payload, and that's what's supposed to come back to the allocator. So again, the allocator needs to get to the header to see what it needs to do. And so again, it can just cast it, for example, to a header star, and then subtract 1 from it. That'll move it back 1 header size, and now it can work with the header on the payload. Okay? So the allocator has to do some pointer arithmetic to do that kind of stuff. Okay? Any questions on any of this? Because like I said, this is what you'll be doing in Lab 3. All right, unless you do something really clever and crazy or different and crazy and try to separate headers and payloads, which I wouldn't recommend. Okay, let's see. If you look at your memory blocks where you have, each one of these little blocks is a header and a payload and the padding, so we're just representing it as a whole chunk. And the dark ones are allocated and the light ones are free. They're available. You can see that if you use the sizes, you can trace through this series of chunks of memory to get to the next one, to the next one, to the next one, and eventually, if you add one, add the block size on the last block, you should end up just past the end of the memory pool that you have to manage. So that would be a good thing to assert, that you can actually, when you end up at the end of it, you end up right at the end of the pool, not like 50 bytes past the end of the pool, because then that would be a bug. Okay? So like I said here, the allocation request comes in, and the allocator can search through this sequence of blocks to figure out which block is actually available. The block may be a lot larger than the requested size. And again, while you're debugging your work, you could always just start out saying, all right, I'll just hand back the larger size. I don't care about splitting the block. But eventually, you need to take that request and figure out, can I split the block? Is it worth splitting the block? Is the leftover going to be worth using? And then just split it, or don't split it, and hand back the split block. Okay. And there are several different strategies you can use for finding that block. First fit is a strategy where you just hunt through the sequence of blocks, and the first one that could be used to satisfy the request is the one that you use. Maybe you split it, maybe you don't, but you just stop at the first location that you find that would satisfy the request. Next fit is, well, I'm going to always remember the last block that I used to satisfy it, because that's probably a good place to start looking for the next allocation request. So that's called next fit. And then best fit requires that you look at all the free blocks. Now, that's with this design. You can come up with better data structures that allow you to go straight to regions that might be good options for your allocation request. But in the design that we have right here, you have to search through the entire thing. So best fit is, I go through all the blocks, and I pick the block that is closest to the size of the request, and that's the one that I actually use. Okay? So these are some allocation strategies that are used. So yeah, when a block is freed, you need to coalesce it if there are any adjacent free blocks. So in this case, we have our fourth block, the block with 71 bytes, which probably would have been padded out to something else. And that one gets released, and so the allocator has to go in and say, well, is the subsequent block free? Is the previous block free? So that it can go ahead and coalesce. And the nice thing is, if your allocator is always doing this, you only have to check the next block and the previous block. Those are the easy ones. If you don't always coalesce, then you might have to look for a sequence of free blocks. But if you have a situation where you're always coalescing, then you just need to check the adjacent ones, and then you'll be done. Okay. Now, in this situation, we can coalesce. And this is the easy situation, because it's a good one to start with. You can see that all we really need to do in this situation is, while we have our current block and we have the next block, all I need to do is add in the next block size to the current block size, and that automatically coalesces. Does everybody see that? I don't have to actually modify the second block, because I can just consume it by updating my size. All right? Yes? Yeah. Basically, the entire second block, which includes whatever header and payload space available, all of that gets consumed by the block that the allocator is currently working. Right? Now, you'll notice, well, if I consume it, which is faster? Zeroing out the next block or not zeroing out the next block?
Not zeroing.
Yeah, not zero. I don't want to write stuff if I don't have to. So this is why when you allocate stuff on the heap, frequently you'll find, wow, there's garbage already in my block. And this is why when you use it, you have to make sure to zero it out or set it to appropriate initial values, because there may be garbage already in the block when you go ahead and start using it. This is why initializing values is so important in C and C++. Okay, so yeah, like I say here, this is only fast when coalescing with the next block. If we have a situation where the block with the size 36 is released, now we have a slight problem in that it's difficult to identify the block that's actually adjacent. Because we know it's easy to check the next one. We can just look at the next one and say, oh, that one is not free, so I can't coalesce it, or else the program will be sad, because suddenly I'll be handing out that block for other things. So the question is, how can we efficiently find the previous free block? And there's a number of approaches, but a really simple one is, note that I could just duplicate the header on the end of each block as well as at the beginning of each block. And so if I have the same header data at the end of the block as I do at the beginning of the block, then the allocator can just, I already had to take one header size step backward to get to the header from the payload pointer. Well, now I just take another step back and I have the previous block's header. So I can look at whether or not it's available. So you're basically taking this implicit free list, which is a singly linked list, and turning it into a doubly linked list by duplicating the header at both the beginning and the end of the block. Okay? It was developed by Don Knuth, who's a badass. And yeah, so it's called a footer, and the whole approach is called boundary tags. Okay? So this is a way that makes it very fast to be able to coalesce with both the previous and the next block in the free list. And if you do this, basically now freeing is constant time, right? And this is the kind of thing that you think about. How long does, or what's the time complexity of allocation? What's the time complexity of freeing? This is the kind of thing that a lot of programs are doing all the time, allocating and freeing space, right? So we need it as implementers of an allocator, we need to make it fast. If it's fast, the programs will be fast. If this is slow, the programs will be slow. All right, any questions? So again, if you do something in your CS24 allocator where you use like one int as your header, then it's real easy to have another int at the end for your footer. And then your coalescing will be super fast. So implicit free list is nice, but we note that when we want to allocate some memory, we have to hunt through all the blocks, even the ones that are allocated, which gets slower and slower if I have a program that's allocating a lot of stuff. So why would I even look at the allocated blocks? Not only that, but we say, hey, guess what? These free blocks are supposedly not being used by the program. So if they're not being used by the program, I can put other stuff in there, allocator stuff, and then I don't have to worry about hunting through all these allocated blocks. I can use the free blocks just by themselves. Okay? So like I say, we really only need to keep the free blocks in a list because those are the ones that we could actually use to satisfy allocation requests. And the program is allegedly not using them. So since we have these observations, we could use a linked list to chain together the free blocks. Okay? So you can see that now our header is getting a little bit larger, or maybe we have a free block header and an allocated block header. So we have part of it that we know will tell us if it's allocated or free and what size it is. And then if it's free, we have a little bit of additional stuff. You could do something like that. And so this approach is an explicit free list, because now the free list actually chains together all the free blocks as opposed to just chaining all the blocks together in some implicit mechanism. Okay? Now, there's a lot of different ways to organize blocks, and like I said, really good allocators have all kinds of clever techniques that are used for doing this kind of thing. So these are some very basic ones. There's actually a paper. It was published in 1995, and it's a survey of allocators. It's a really good paper. If you love this kind of stuff, you expect to take the operating system class next year when we offer it, then you should find this paper. I think you can just search for Wilson 95 allocator on the web, and you'll find it. But it's a pretty beefy document, and he goes through and talks about all kinds of explicit allocators. He wrote another survey that covers all the implicit allocators, garbage collection, and so forth. So anyway, so here's one possible approach. Maintain a free list in last in, first out order. So you always keep track of the most recently freed block. Now, when you're putting an entry onto a linked list, it's really fast to always put it on the front because you have a pointer to the first node in the list, and you can always just say, okay, old first node, you're now the second node. The first node points to it, and the new anchor of the list is going to be the thing that I'm just adding. So it's always easy to put it on the front. So last in, first out, you can implement that very simply, and then just take that off. So you just go through, find the first thing that will satisfy the request. That becomes the block that I used. Maybe I split it. I can put the split part of the block back onto the free list. And like I say, even though the free list is in last in, first out order, which is not in address order, so now I can't really traverse it to coalesce, I can use boundary tags, and that'll make it easy to figure out if I need to coalesce with either the previous block in my memory layout or the next block, or both. It's certainly possible you would have to coalesce with both. If you have like free, allocated, free, and then the allocated one is released, now I have to coalesce them all together. Okay? So like I say here, this is a very fast approach, but in research has been found to be susceptible to memory fragmentation. Another one is to maintain your free list in address order. But you can imagine that if you maintain your free list in address order, now you're going to have a bit of an expense when blocks are free, because you have to figure out where to insert the free blocks so that you can actually keep them in address order. Now I say insertion sort, that's probably not the ideal way of doing it. It would probably be best to maintain heap. That's the problem, is now this term heap is used in multiple ways. But there's a data structure called a heap that is a balanced tree that you can maintain an array very efficiently. And you can use that to keep your free list in address order relatively easily. Okay? So that's another option that has been explored. Another one that actually turns out to be widely used is to say, well, programs tend to allocate chunks of memory that have specific sizes, so why don't I go ahead and maintain chunks of memory or groups of chunks of memory that are all similar size. And so you end up with this thing called segregated fits, where you have multiple free lists, and each one maintains a particular size class. So I have small chunks of memory, and slightly less small chunks of memory, and now I have small to medium chunks of memory, and so forth. So you actually have various lists of free blocks. And the idea is that when I want to allocate a chunk of memory, I can exclude a whole bunch of regions that I know will not be able to satisfy it. So when I say first fit strategy, we're kind of doing best fit, in fact, because we go straight to the size class that would be appropriate for the allocation request, look through it, and if there's nothing in there, we go to the next larger size class. So we're kind of building in best fit in the way that we're managing the lists of free blocks. And of course, when we find a block, if it's too large, we can split it and then put the free part into the appropriate size class. And so you get pretty efficient allocation requests. And you no longer have to sort or search through all of the free blocks with this approach, and it really helps avoid memory fragmentation. When you free memory, you coalesce adjacent free blocks. So again, you probably use boundary tags to make sure that you can coalesce efficiently. Figure out, okay, what blocks did I just remove from the free list of the appropriate size classes, and then you add the new block that just got freed into the appropriate size class. So you can do all of these kinds of things. This is very common. When I grew up, this was like the bread and butter of the Linux heap allocator. And I'm pretty sure it still does this. I haven't looked at it in quite a while, but this is a very common approach in modern allocators that are used. This is why you can allocate and release memory all day and you don't have too much trouble with fragmentation. Okay? Questions? Do I expect you to implement segregated fits for Lab 3? Please don't. I think one guy in all the history of CS24 tried, and he turned it in late because it didn't work right away. So just why set the bar way up here when the bar could be down here and still get a good grade on the assignment? So I would not recommend implementing this. You'll have plenty of opportunity to experiment with that in the OS class if you decide to take it. Now, so you can see that dynamic memory allocation gives us a lot of new power. We talked about these various ways that we can benefit from heap allocation. The memory lives beyond the lifetime of the function call. We can do really clever data structures now beyond what we can do on a stack. But obviously there's some challenges as well. And so like I say, heap management is a hard problem to solve. We don't want other programs to have to solve it all the time by themselves. So providing a general facility where some intelligent person has thought about how to solve the problem, all the programs that you run on that system will now benefit from it. So you can see why we'd like somebody to solve that problem for us, and then everybody will benefit from that clever thought put into implementing it. Now, that aside, I also want to point out some of the things that you need to think about when you use the heap. And these kinds of things always make an appearance on the midterm, so pay attention. You'll benefit. Like I say, your code that performs allocations and deallocations of varying sizes are the ones that really suffer from memory fragmentation issues. I ask this question a lot, and I'm sometimes dismayed at the responses that I get. But if you have a program that always does allocations and deallocations of one size of memory, like I'm always allocating 32-byte chunks of memory. That's all I do all day long. And I allocate some, and then I free some, and then I allocate some more, and then free some of the other ones I add. I will never have any fragmentation issues. Everybody believe me. Because remember, fragmentation is about trying to find a place to satisfy that allocation request and not finding it because the free memory is all spread out. And it gets spread out because you allocate large chunks and then small chunks, and then you free the small chunks and ask for more large chunks, or whatever. You have mixes of allocation request sizes, and the allocator doesn't place them properly. That's where you get fragmentation from. Okay? Make sure you understand that. Now, if I allocate a whole bunch of large stuff, and then I free all the large stuff, so there's no more large stuff allocated, and then I allocate a whole bunch of small stuff, and then free it, and then I allocate more large stuff, am I going to have fragmentation? Yeah, I said if I free everything, I won't have any issues. All right? Make sure you understand these things, because that'll help you when it comes to exam time. Yes, so I already talked about that. Code that always allocates and deallocates blocks of the same size won't suffer from fragmentation. But there is a cost. We already saw just a little tiny bit of it, and you'll get a little bit more detail as you write your own allocator. If I have an explicit free list or segregated fit strategy or an implicit free list or whatever I do, there is always overhead when I go in to say I want this chunk of memory. Because I have to record, okay, now this memory is in use. And then when I free it, I have to go in and say this memory is no longer in use, and now I need to coalesce, and I may need to update other bookkeeping values. Okay? So if I'm doing a lot of allocation and I'm doing a lot of deallocation, there is a bookkeeping overhead that comes with that. There's also the overhead of the header. And so if I allocate a ton of tiny objects, I lose a lot of space just to the headers. Everybody got that? Am I losing anyone here? Because this is going to all be very important. I'm taking extra time to make sure that I help you out on the midterm. Okay? So these are all details you need to think about, implications of how heap allocators work. Okay, so enough about that. Think about it, noodle on it, meditate, whatever your kind of deep thought is, and you'll do pretty well on the exam. Okay, let's see. So stacks, yeah, you can see faster and simpler. I don't want to spend too much time on this, but we'll just touch on a few of these things. The stack is much, much faster than the heap because, again, we know how much space we need at compile time. So we can omit exactly the instructions to manage the stack pointer. Make space for it, release that space, all of that kind of stuff. The heap is more powerful, but it's also slower. And so sometimes you'll look at a program and you'll say, oh, why are you allocating this on the heap? You use it inside of a function call, and you release it at the end of the function call. And it's always a fixed size. Why do you use the heap? It'd be faster to do it on the stack. Okay? So you can think about those things as well. The stack is different. It's faster, but it's simpler. You can't use it in all the same situations. But if you have a situation where you're using the heap in the same way you could use the stack, just use the dang stack. Use the stack. Okay, enough ranting about that. Let's see. So yeah, we've already started to talk about this whole optimization topic. We started talking about it when we introduced the notion of data alignment, how we always read memory in this particular size. So let's think about maybe making our programs take advantage of that. There's two optimization principles. One is making the common case fast. So if we look at what computers frequently do or programs frequently do, like, hey, function calls. We like function calls. Programs make function calls all the time. Let's try to make that as fast as possible. Okay? Then that's making the common case fast. And then you have another sort of parallel principle, which is make the fast case common. And this is the one that we're going to see more and more as we go through this stuff. Okay? The hardware is good at certain things. And if it's good at those things, let's write our programs or generate our programs in a way that makes those fast things the most common situation, which is why we do alignments and stuff like that. Okay? So make the common case fast, make the fast case common. You're going to see this a lot. So, Yeah, the compiler and assembler will adjust the layout of your program. I mean, that's if you're not writing it by hand. If you're writing it by hand, then you have to adjust it to do this, so that we can take advantage maximally of the way that the processor interacts with memory. Yeah, that's why we had these P2 align 415 things in here. Okay? That was aligning the function calls to be at the start of address boundaries. Because, hey, when you call a function, the processor needs the instructions, so it needs to load them in. And if it can load them in with as few reads as possible, that makes us happy. And that makes our program fast. So we have these kinds of things. And you probably even saw it with the fact code that you saw in assignment 2, that there were these like dot align things at the beginning of loops. Same thing. In fact, it's kind of funny. The compiler will actually insert no-ops, I think, in the space, the intervening space. So no-ops are basically, there's a particular instruction on IA32, NOP, and it's like a skip. It basically does nothing. And its hex code is 90, if I remember correctly. And when you have it, the processor sees it, it's like, okay, I'll do nothing, and go on to the next instruction. And it can insert those and make sure that the starts of loops are word aligned and so forth, so that all of this execution will be fast. All right, yeah, same thing happens with data structures, and we've seen some of this. Hopefully you've heard of structs. If you haven't, then you're going to have a fun time in CS24. But structs are basically heterogeneous. So instead of being like an array where every element is the same, now you're saying I have multiple elements, and they can be different if I want them to be. And like I said, the members can be primitives, pointers, arrays, other structs. We can have all kinds of stuff inside of structs. Members have their own names as well. So here's a linked list node. What size are all the values here? 4 bytes, right? We have 4-byte number and 4-byte pointers for these things. We can use it like this, so you can see that we're going to be encoding some values in here, hard coding values. So struct node n, and number is 42, and string is the answer to the question of life, the universe, and everything, and next is null, because I guess we have no other questions. What the compiler does for this, when it sees your struct declaration, is it runs through and figures out what is the size of each one of these elements, and from that, it infers what the offset from the start of the struct that member should reside at. So you have number, obviously being the first thing, will be at offset 0. Its size is 4 bytes. The string is at offset 4 and is 4 bytes. And the next pointer is at offset 8 and is 4 bytes. And so the compiler keeps track of this stuff, and when it generates code to access these members, it inserts the appropriate offsets using our indirect access mechanism, which is why this stuff is so cool. So we see init, it takes a struct node star, and our generated assembly code, you can see that 8 EBP is n, so that's the pointer to our node. It loads that into EAX, and then it uses indirect access, indirect addressing based on the value in EAX to access the various members. So 42 goes into the address that EAX points to. Our string constant goes into EAX plus 4, and our next pointer, null being 0, goes into EAX plus 8. Super simple, right? Okay, so that's how we would have code that accesses stuff. Now, here we had 4-byte members, but we can also have things like char, or car. I don't know how you pronounce it. Who says char? Like some of you. Who says car? Who doesn't pronounce C-H-A-R? There's some who are left over. So, yeah, I say char. That's just how I grew up. It's a character, I suppose. But anyway, if the compiler used only 1 byte for this member, then you can see that we'd have a real problem with non-aligned access now. So what the compiler does is it makes the fast case common. It adds extra space into the struct. Because I've said this before, typically we need to conserve time more than we need to conserve space. It tends to be that time is more expensive than space, so we try to maximize or minimize our time requirements by increasing space requirements. It just turns out to be cheaper. So the compiler will pad this struct, that's what we call it, it's padding. And if you want to know what happens if you access or write to bytes 5, 6, or 7 in this struct, nothing happens. You could use that space for something else if you really wanted to. You won't get any approval from me for doing it, though. So you can see that CH, though, is followed by 3 unused bytes. And if you were to look at the assembly code now for accessing this thing, you can see that the red highlighted line, we say for EAX, so we still have word-aligned access, but we use a move B instead of a move L, because we're just accessing the 1 byte. Okay? So that's what's happening under the hood. And also, if you were to do size of, you would see that it says 12 bytes and not 9, because the struct takes 12 bytes, even though you really only need 9 bytes to store all that data. All right, everybody with me? Okay, so it is possible to get these things to be packed. It's really not a good idea. There's really just a few rare circumstances where you want to do this. But as an example, you can specify a packed attribute on GCC to tell it to not pad out these values. And it will actually generate a 9-byte data structure. And if you were to look at the generated assembly, you would see, oh, now it's still doing the move B97 for EAX, but now it's using 5 EAX instead of 8 EAX to access this code. Okay? So you can do this. But the problem is that this is going to be a lot slower, especially if you have an array of these non-padded structures. You can see, for example, 5, J is, the first element's J is not aligned, the second element's I is not aligned, and even all the way up to CH and J also in the second struct will not be aligned. So you have a problem that if you do this kind of thing, you're going to run into trouble, performance issues. And so you want to do it as infrequently as possible. I have here the basic situation where you might want to do this if you're trying to break apart a data structure that's stored on the file system or being sent through the network. You would use a non-padded structure to read in that value or that set of values and then immediately stuff it into something that's padded so it's much faster to work with. Okay? Let's see, yeah, so even if the small member is at the end, it'll still pad it because the compiler's thinking about other stuff besides just that struct. So if you have a situation, for example, where you have other local variables or you have an array of these things, it's going to still go ahead and do some adjustment for that kind of thing. Which, if you think about it, you can see that you can waste a lot of space by doing this kind of thing. It might be smart if you had this kind of situation to have the struct only contain I and J and then move the character somewhere else, especially if you're going to have an array of them. Then you could have a struct of just ints and it would be fine, and an array of characters, and then it would be really, really fast to access. These are the hoops sometimes you have to jump through because the machine, even though it presents this abstraction of an array of bytes, it's not really that way. Okay? Any questions? Okie dokie. So that's structs. Let me see. Yeah, fast case common. So we talked about that. Unions. Who here has used unions? Who's heard of unions besides like the state of the union? All right. Unions are a very interesting beast in C and C++. Unions basically do the same thing as our structs, except the starting offset of all the members is 0. So think about what that means. Like you say, all the union members occupy the same memory location. So that means I have multiple ways of interpreting the same chunk of memory. Why in the world would we use this? Okay, so you'll notice here that the way that the compiler would treat this is you'd have the int val member, the str val member, and the float val member. Offset is 0 for all of them. And the size is 4 bytes for all of them. So what this, and so you can't have things like you have a float and a double and an int and a long where they're different sizes. The size of the union will be the size of the largest member because all the members actually overlap in space. Okay? A little bit weird. Why would we need this? Yeah, I have an example in the next slide talking about this. Like I say here, it's very useful when you want to represent different kinds of things where you expect to only use one of them at a time. Okay, like I say here, mutually exclusive kinds of values or tagged data structures. You tend to want to avoid doing this. You need to do this if you're writing an interpreter, like the Lab4 scheme interpreter does this. Okay? If you're writing Python or if you're working on Windows and you're interacting with Visual Basic or Visual whatever, then you can run into this as well. They have a type called variant, which does exactly this. Okay, so yeah, typically use them in a tag field because you need to have some way of knowing which of the union members is actually the correct way of interpreting. You can imagine if you stored the int in one piece of code and then later on you tried to interpret it as a string pointer, you'd be really sad. You'd run into trouble because it's not a valid string pointer. It was an int. Okay? So there's a little type value that's frequently included that is used to tell what member is actually the one that I want to use. And so you'll have code like this. If vtype is int value, then I want to access v_int val. Okay? And a lot of times you'll have a switch statement that says switch v_type, and then based on the various cases, we'll handle the appropriate member of the union. All right? Questions? Like I said, this is very common in interpreters if you're implementing an interpreter in C. And when we get to lab 4, I wrote a scheme interpreter just for that lab. And I'm not sure it was the best idea, but I did it. And so you can look at the implementation if you're curious and see how these various things are managed. In fact, you will have to think about it a little bit, because part of the code you have to look at is, in fact, the value representation. Okay, so yeah, C is a low-level language. We know how to do most of C now. Go us. There's a few things that we're going to talk about next week that C can do that we still have no idea how to do. So we'll talk about those next week. But we've basically covered the bulk of C and how we might translate it down into assembly code. And of course, the assembler takes care of the rest. So this is nice. There aren't very many runtime facilities. C does have a runtime. C++ does have a runtime, but it's like the allocator, and that's kind of all you have. C also doesn't stop you from being dumb. Here's an example. You have int A, int R is 4, of size 4, and then you have int B. And you are certainly allowed to write to R4. You're also allowed to write to R minus 1. It will let you do that. What will happen? Maybe it'll write to A. Yeah, maybe it'll touch stuff in the frame like the caller's EBX or EBP. I'm sorry, I misspoke. Maybe it'll touch the return address. You don't know. Because A and B might be in registers. That's part of the problem. Also, part of the problem is we don't know exactly how the compiler will lay out the local variables if they were on the stack. Because I don't believe that there's any requirement in the C standard about the addresses of these things. When you have a struct in the C standard, I believe that it says that the members have to have addresses in the same order as they're declared. So if you have A, B, C, the address, the way it's laid out will actually be A and then B and then C, even if you have padding inserted. But in this case, we don't really know. So you could end up with stuff changing. And this can lead to all kinds of fun. Buffer overflows. You've probably heard of buffer overflow exploits. We're going to talk about them briefly. Let's say that we have a program that has a character buffer that is on the stack, so it's a local variable. A 100-byte buffer can certainly fit on a function stack frame. And then we call the universally hated, and for good reason, getS. And we pass it the buff. And what getS is supposed to do is read from console input and stuff that into whatever buffer that you've provided. Now let me ask you a question. Does getS care what size the buffer is? Not right now. Not ever. It's a C standard function. Yeah. Never use getS. If you do, I will hunt you down, smack you in the back of the head, and then fly home. So yeah. So getS buff, you can tell. I don't even pass its size in the argument. And so we have here, get the current character. If the character is not EOF and it's not a new line, stuff that into the array and move forward. And finally, we zero terminate the string. There is nothing here that cares about the size of our character buffer. getS was one of the worst ideas. Some people would probably put that right up there with the concept of null. You know, having null pointers. But yeah, getS is a terrible idea. So I should say it is a common source. Not really, not anymore, because people realize that getS is really dumb. But if you ever find code that's using getS, it's a horrible piece of programming. You need to use this other one called fgetS, where you actually get to say the size of the buffer that you're saving into. Okay? I don't know who came up with this, but it wasn't their best day, for sure. Okay? But if you have code like this, now we start having problems, because it's not that we just can overwrite the array and crash the program. We can now start doing other things. Here's one. I crashed this server program unexpectedly when fed bad input. Anybody heard of ping of death? No? This is the kind of stuff that I would do when we were undergrads because it was fun. I mean, I never did it. Other people I heard did this kind of thing. But what it was, and it was particularly targeted at Windows, because Windows was a notable example of where we had this problem. When you send an IP packet that's above a certain size, a lot of times routers will fragment it so that the smaller pieces can be sent and it'll be reassembled on the receiving end. Well, the problem is that IP packets are supposed to only be a maximum of 64 kilobytes. And OSs, expecting that this would be the case, would have a buffer that was exactly 64 kilobytes. And so what you could do is, with various programs that were floating around, you could send people's computer a packet that when it was reassembled would be larger than 64 kilobytes. And on Windows, it would instantly result in a blue screen. Yeah, and we would do this to each other. It was fun. But the thing is, like, you think, oh, Windows, how terrible. What an awful operating system. Linux had this problem. The Apple, whatever the Apple operating system was at that time, also suffered from this problem. It was a common issue. So you overflow a buffer, and boom. It's in the kernel, so the kernel panics and your system dies. No. The routers are really not capable of seeing the global picture. And so that's part of the problem. You could easily have these fragments go on different routers and end up at the same machine. So the router, being simple and maintaining as little state as possible, wasn't really able to filter this. Trust me, OSs really don't have this problem anymore. You can also modify program state. Let's say that you had code like this, where you have our buffer, and then we also have some flag that we use to tell if we're allowed to do something or not. Conspicuously named authorize. Well, if we had a situation where this was laid out on the stack, you can see one of the things that can frequently be confusing to people is when you lay out these buffers, the lowest index is lowest on the stack because I want to add offsets to get to the higher indexes. So the last 4 bytes of the buffer are right before authorize. If authorize happens to be on the stack, it probably would be in a register, but if it was on the stack, we'd have a problem. So if somehow I could overflow that buffer and put a value into authorize, then I can make this program do something that it wasn't really written to do. Everybody see that? So that's one kind of way that you can use buffer overflows. You modify program state. The much worse one is arbitrary code execution. And this is sort of the holy grail when you're trying to crack a program, is you try to find a way to hit the return address. Because most likely authorize won't even be on the stack, but the buffer will be. There's no register large enough for the buffer. And if you can target the return address, then that means that you can tell it to jump somewhere else. Now, how in the world would you do that? This is part of the challenge. Because if you think about it, I'm trying to get a program that I didn't write to jump to a location, and I'm going to try to get that location to be something I can control, and I'm going to try to write data into that location. How do I do that? So there's actually a technique, which I don't mention in the slides, but I'm happy to describe it, called a no-op sled, or no-op slide. I told you about this no-op instruction, hex 90. What you can do is you can send a whole bunch of no-ops, and at the end of that code, have the stuff you want to run. Well, now you just turned your target into a really large area. Okay? All I need to do is to get the program to jump somewhere into that no-op slide. It slides through the no-op slide till it hits the code that I want to run. Okay? So these are techniques you can use for arbitrary code execution. Okay? This is why Linux has a whole bunch of things preventing you from doing this now. It will put what are called canary values. You know, like the canary in the coal mine. If the canary dies, get out of the coal mine, because you're probably going to die if you stay. Okay? canary values at the beginning and the end of your stack frame. If they get overwritten, your function's probably been compromised. And also they will adjust the placement on the stack and vary it randomly so that it's difficult to know what address to jump to. Okay, so these are some of the techniques that are used. Any questions? Don't try this at home. Okay, yeah. So, but yeah, this is actually, these kinds of issues can occur in the heap as well. You have function pointers used in interpreters. JavaScript is like everywhere now, and we JIT compile stuff. We JIT compile Java, which means that when we have this stuff on the heap and we're treating heap data as instructions, you can compromise that as well, and you can do arbitrary code execution exploits as well. Okay, so I just want to make sure that you understand all this. Okay, so I won't talk about this in very much more detail because you can see that obviously there's complexities in this, but like the vast majority, I say a very large percentage, the vast majority of exploits are actually buffer overflow exploits. So how can we actually design a system that doesn't suffer from these things? Yeah, so I'm going to mention memory leaks as well. Memory leaks are a problem that we can have. In fact, most programs, if they grow large enough, start to suffer from memory leaks. It's just difficult to avoid. And so what we'd like to do is start figuring out, well, what facilities can our programs leverage so that we can make them a little bit more reliable for writing code. Okay? So implicit allocators are one of the next things we'll talk about because that sort of mitigates the issue of memory leaks. To some extent. There's still some challenges you can run into. Okay, but garbage collection, reclaiming unused or no longer used heap storage, I should say. You have most of your memory leak issues start to disappear from that. And similarly, we have higher level language facilities that we'd like to introduce. And like I say, our C doesn't really allow us to write correct and bug-free programs very well. So what we're going to do is start going up the abstraction hierarchy a little bit more and start looking at how we can mitigate some of these issues through language features. And so next week, we'll get to, this is sort of my fun week because we'll get to go through a bunch of interesting topics. We'll talk about implicit allocators and making pointers opaque so that we can't manipulate them anymore the way that we have been. That also eliminates a huge number of issues. Like if I can't have a function pointer, I can't call arbitrary code. Okay? Object-oriented programming and polymorphism, we'll talk about that next week as well. Probably all of you have used this in one way or another without realizing it, or maybe realizing it. And we'll also talk about exception handling, because that's just really neat. Okay, any questions? All right, we'll see you next time.